Okay, yeah. So it is our pleasure to introduce Haichen Shen. So this is going to be the last guest lecture we have for this workshop, and what a better way to end other than learning lessons learned from securing Scroll zkEVM. So without any other delays, please Haichen, take the stage.
Yeah. Hello, everyone. I'm Haichen. So I'm co-founder at Scroll. So today I'm going to share some lessons we learned from securing our Scroll zkEVM circuit. So it's more like about the ZK circuits, as I think like everyone here is for to learn more about ZK. So I'll share some of the experience we've done to make sure our zkEVM circuit is secure. And then like during the talk, feel free to chime in and ask any questions or just post your questions in the chat, so I will answer any questions you have. So for those like who you're may not familiar with zkROP or layer 2, so I'll give like a very brief introduction about how layer 2 works and then what is like a zkROP does. Excuse me. So you can think of like a layer 2 chain is a parallel chain along with the layer 1 chain, which is the Ethereum. So the layer 2 chains can process things more fastly, and then it can process more transactions, and then in a more cheaper way. But in order to become like for this parallel chain become a layer 2, what you need to do is that you need to upload, you make all of transaction data or some data available on the Ethereum, so that you can inherit some of the security features from the Ethereum by having all of the states, so that everyone can reconstruct your layer 2 chain state from the data you have posted on the Ethereum. And then so Ethereum can be also the final settlement if there's any dispute or anything like the wrong happens with the layer 2, so that you can always try to claim back your assets to the layer 1. So this one step you need to do every time is that you need to post some data. It can be either transaction data, block data, and also it can be some state diff. So it depends on different types of layer 2s and then the design. So this is like something like going to happen. So usually what happens is that after every some period of time, so you collect enough the transaction data, and you will post in the single transaction that's sending all of the transaction data to the layer 1. And though that could be happen like within minutes, or like this, sometimes like it can be happen in the longer term. So in a scroll, you're having like every a few minutes, you'll see like a transaction sending all of the transaction data, like of that batch of transactions to the Ethereum. And after those transactions, data inside those blocks has been submitted to the Ethereum. So we consider like those status of those blocks. It transits from the pre-committed state to a committed state. So that you can see like after this time, so since the data is already posted on the Ethereum, then people can try to reproduce, like if the people trying to get faster finality, doesn't want to wait for the proof, then people can try to just using the data, reading the data from the layer 1, and trying to reproduce the state, the new state root, and verify whether all of transaction has been processed correctly. And then things like it get slightly different. There's two type of the things like that. For a rollup, you need to also have some sort of the proof to prove that all of transaction has been processed correctly. So you don't only submit the data to the layer 1, you also need to have some proof, so that to make sure that the people can trustedly use the latest state root of your layer 2 status. So for the zkROP, it comes with a validity proof, which will be saying like we're using the ZK circuits to prove that given all of the transaction data I posted on the Ethereum, so I correctly apply the state transition functions and I prove that it's correct, and then so the state root transit from the old Merkle root to the new Merkle root. So that's why like that. So the validity proof usually takes like a few minutes, or like tens of minutes to process, so that it will be submitted a little bit later to a later blocks. And after the validity proof is submitted to the layer 1, then that means these batch of transactions in these blocks has been finalized. So then, so people can trustlessly use the new state root after applying those transactions. So people don't necessarily need to do the recomputation, reprocessing of these transactions. People can just trustlessly use the use the new state root after the validity proof has been finalized on the Ethereum. There's slightly a different type of layer 2s, which is the optimistic ROP that will be waiting for 7 days. So you're just being optimistic so that I assume that the give like good trust was like the face into the layer 2 operators so that they process those transactions correctly and it doesn't create any invalid transactions. So it will open a challenge window for 7 days so that people can try to reproduce the state and see if it sees like the state root is different from what they see like from what they locally computed result. Then they can send a challenge proof, a fraud proof to challenge the state that posted on the layer 1. So that would be like take a longer time. Like you can think of like it's a week versus like an hour or like less than an hour, like compared to the optimistic ROP and the zk ROP. Okay, so the score is a zk ROP. So we're building a zkEVM circuit. So we're building a EVM compatible zkEVM circuit so that the developer doesn't need to change anything like what they use. They can use the vanilla Solidity compiler and then like whatever library they are using and the SDK they're using, they'll be directly compatible because we are at the EVM bytecode level compatible and equivalent with the Ethereum. So there's a lot of things people doesn't need to change. So we hide all of the complexity by putting the EVM state transition function into a ZK circuit. So that's like what a need to do is like you need to, for the ZK ROP, you need to generate a proof of validity that basically you're putting the program, you're constraining this program using a ZK circuit. And here the program is basically the state transition function with the Ethereum virtual machines, which we call like EVM inside a circuit. And the input to this function will be the old state root, and then a batch of transactions you need to process. And then you will also need to prove the output, which is the new state root. You need to prove that this state root transition is correct. To be like more specific, what you can see like this is the state root. Once you give the state root, it will determines a state tree, which include all of the accounts and then the contract storage. And you give like a few transactions to this EVM machine, Ethereum virtual machines. It will have like a state machine inside that processing the opcode by opcode. And also it have some transit memory, including the memory and the stack. And it also can read the bytecode, which is the smart contract you're going to do. And it have like access to the storage, which is determined by the state root here. And after you execute this virtual machine, you will get an execution trace, which like have from step 0 to like up to n until like you finish execute the smart contract there, and then you will then end up getting a new state root here in the worst state root at the timestamp t+1. So what the zkEVM does is that it takes the spec of the EVM, and then you encoded all of the constraints to constrain the correctness of the execution of this EVM, and then it takes these 3 as the input. Basically, it's the old state root, the transaction you're going to process, and also the new state root, which is the output. So usually, like in a ZK circuit, both the input and output will be the public input to the circuit. And then you're taking the execution trace as the witness. And then what you do is that you constrain every step, like you execute upon the bytecode is first you need to constrain that is executing the correct bytecode you read from smart contract, and you need to constrain and prove that at each step the opcode is being executed correctly inside the zkEVM circuit. Okay, so any questions so far? That's like almost like a quick run through of like how the ZK ROP and then what the zkEVM circuit does.
I have a quick question. So basically, the circuits that you are building, it's pretty much whatever the opcode operations, right? So the
Yes.
basically mapping the opcodes to a circuit.
Yes, correct.
Okay.
Yep. So also give like a little bit more details as like you can think of like we have so the zkEVM have a bunch of sub-circuits. So there's one sub-circuit for the EVM circuit, basically it will mapping the step here, like each step will allocate a few rows to constrain that this step of the opcode has been executed correctly. So you basically, for example, if it's a calculation like a multiply of 250 big word, then you need to constrain like the multiplication is done correctly using the ZK circuit and constraint. Okay, so if there's no more questions, then I'll move to the second part. I'm going to share some of the practices we've done, like in the scroll to secure our zkEVM circuit. So first of things like also give like a quick highlight of that. So our scroll zkEVM circuit is built on using the Halo 2 proof systems. So it's built by the ECC or the Zcash, the company or the team behind the Zcash. So they write this very great proof system, Halo 2. It gives us a lot of flexibility. It has a plunkish front end and so the backend originally they have is they're using a different PCS, but we replace using the plunk with the KZG polynomial commitment. So the whole entire zkEVM circuit code base is very large. It's almost, I think, more than 90,000 lines of code. So it's a very complicated circuit and a very complex system. So it's very hard to guarantee the security. So it's a very challenging job, I would say. And then also we use a bunch of the complex properties to optimize our circuit, now including the dynamic lookups and also the random linear combination. So usually the lookup argument we use is lookup fixed lookup tables, but here we are going to in our circuit we're using a dynamic lookup. Means that the lookup table is also constructed from the witness synthesis, so it can be vary over the different instances of the circuit. It's no longer a fixed lookup table, but this can help us. Like the dynamic lookup basically can help us connect the two different circuits. So there's one circuit we're going to provide or constrain the lookup tables, and then the other circuit will basically look up to see if I can find a matching entries from this lookup tables that is dynamically constructed. And then another thing is like we're using the random linear combination, which can help us handle some dynamic lengths of the buffers you have. So that's another thing that we use to handle the dynamic, a lot of dynamic variable lengths opcodes inside the virtual machine. And then also another thing is like a challenge we have is that we need to implement the EVM in the zkEVM circuit with high equivalence. That means like every opcode and pre-compiled, we need to match the behavior of the EVM, including a lot of different corner cases. Because if you look in the details, there's something like, for example, where you do some memory copy from the core data, transaction core data to the memory, then there will be automatically padding if you copy it's out of boundary of the core data. There's a bunch of like some small like details there. Like you need to match a lot of things like the corner cases from the EVM specs into the ZK circuits, which gives like a lot of complexity because there will be some branch logic, condition logics there. So you need to consider different branches, and in certain corner cases, you also need to handle. So this is also another challenge when building the scroll zkEVM circuit. So another thing, one last thing I want to highlight is like this circuit has been like building the open source, building the open like from day one, and it has been collaborating with a bunch of open source collaborators, including like the Ethereum Foundation PSC group, and also we also work with Axiom. So they wrote a very great library called Halo 2 library, Halo 2 lib, that also provides a lot of ECC, very well optimized gadget for constraining the elliptic curve operations like ECC, and also the things like built on top of that, like pairing circuit. So there's like a bunch of collaborations in the open source. And I also want to credit to all of the community members there. Okay, so now let's talk about the practices that we have been like committed to do in building the zkEVM circuit. So first of all, as I mentioned, so the circuit is being built like in the open source from day one. So all of the PRs has been 100% peer reviewed. So there's kind of a snapshot from like a PR that has been commented and then reviewed by others in the community members. And then the second thing is like we also have strong crypto team in the school, and we have been doing continuous reviews in-house. Especially, I think a few months before the mainnet launch, has been doing like all just internal reviews and then cross-reading others' code. There's some like a snapshot I shared here, which shows like, okay, so this is some bug we found internally and to fix. And also there's like some share like this, okay, so there's something like that we didn't consider, so we probably need to fix it, like the some is like bug or completely bug there. And the third thing like I need to do is doing extensive testing. So it's really needed to like test all of different corner cases, because there are so many different cases like you need to consider from the Ethereum. As the EVM itself is already a very complicated software. So there's a lot of corner cases, and there's like something like the it's very complicated and also very hard to think about. So the good things like what we have is that Ethereum itself like provides a very extensive testing list. So this is something like a snapshot of all of testing we run. It's all like in total you can see like the 17,000 of the test cases contained in this EVM test tool test vector, and then it has like 17,000 different cases, and we have like some cases that doesn't like even be like the practical to reproduce in the real world, but they also included that. So this is a very good practice for us. Like there has a very extensive test cases like for us to run through, to getting like all of like the very high pass rate or like a success rate is pretty challenging. And also we see like doing the testing like after finish the development and then run through this like initially, okay, we can see like that there's maybe like 5% of cases like we are failing, and then there's cases we didn't consider. That help us like to find out a lot of completeness bugs. So you can think like different corner cases and semantics differences. And then I would say like even though like we run through this all 17,000 test cases from the EVM test vectors, it's not even like enough. Like we actually find we also have been running our testnet for like months and months. Like we have been like running like almost a year through a few iterations of the testnet, and then we basically like before the mainnet, we basically replay all of the transactions we have like collected from testnet, and to test over through our circuit to see if we can correctly constrain and then prove the state transitions. And then we do find some additional cases after passing this test tools. We do find that some additional test cases like that doesn't even like being like found inside the EVM test vectors. And then we found the additional errors like we encounter in the real world but not covered by the test cases. That means like I want to say like the shares like that we definitely need to do like very like the testings, more testings like to make sure like your circuit is correct. Like so before like maybe like this better method, for example, if you can do formal verifications, maybe they can give you stronger guarantees. But before that, definitely like trying to see like if we can do like more testings to make sure the circuit is correct. Especially like for the circuit like we are building, it's the EVM circuit, zkEVM. It's very complicated, so we need to make sure that it's correct. Okay, and then the last things like we do is like we contract with external auditors, like top tier auditors, been looking and vetting our code to see if they can find any things. We've been working with like Trailblaze and Zedek and Kalos. So been looking over our Scroll zkEVM circuit, and some of the part of the circuit has been reviewed by both of multiple teams to have overlaps, so that we make sure like they have been looking, doing like independent and external effort to looking at the circuit to make sure like there's no additional bugs we have. And also we're going to have like some additional open source bug bounty on our zkEVM circuit, so that there will be like expanding, having more eyes up to look at your code to make sure like you have hit all of the bugs, like find the bugs and then inside the circuit. Okay, any questions so far? Okay, so if not, like I'll move on like to the next part. It will be sharing some of the bugs we found inside the zkEVM circuit, doing all of the practice as mentioned before. So mainly I think like there are 4 categories like in high level of the bugs inside the zkEVM circuit. So it's also like I think in general like apply to most of other ZK circuits you have like the develop. So this first is under constrained variables or under constrained cells. So this like I think the most common but also very critical bugs you have. Like it covers a lot of different cases, including I think the missing ring checks. So the missing ring checks should be like a part of the under constrained variables, because you need to think like every value you have inside the ZK circuit is inside a finite field. So anything you can wrap around. So if you don't do proper ring checks, then that means like certain things like you saw like the constraints correct, it may be like a missing the points, like you didn't consider, okay, so if the variable is not within the range you expect like the cell to be, then that means like the constraint written can be violated by, can be found some complicated cases to violate. Basically you can find like a counter cases can also satisfy your constraints. So the under constraint variables and then missing range checks are like a very like common errors. So sometimes it's very it's hard to find as well. Like with some logic it could be complicated, and then there'll also be some logic errors. So this logic errors is when you write complicated circuit. So for example, when we write a circuit, take an example of the RLP encoding. So there's like an encoding schema inside the Ethereum. So doing like this RLP encoding. So what how we constrain the RLP encoding inside the circuit is that we build a state machines. So trying to mimic the logic of this encoding logic, and then using a state machine, like they're trying to transit from different state. And there'll be some like a logic error. So if you didn't consider the state transitions from one state to another state correctly, then there'll be some logic errors, and then there'll be some loopholes you can find inside the circuit. And then the last one will be like is the semantic alignment with the Ethereum virtual machine. As I mentioned, the EVM itself, like it's very complicated and different corner cases. So you need to hit all of the corner cases correctly, and then make sure the semantic will be aligned with the EVM, so that the transaction, if processed correctly by the EVM, should be also passing your circuit correctly. So overall, like you can think the third category here can be like is most like soundness bugs. And then the last two actually, so the logic error can be sometimes soundness bugs, sometimes will be completeness bugs. And then some alignment, misalignment will be also completeness bug. So the soundness bug means that you can find another counter cases that can also satisfy all of the constraints, but you can basically provide a fake witness that can satisfy your circuit constraints. And then the completeness bug is that everything like you can pass like from your application logics can be also passed through the circuit. Okay, so one case study, like I'll provide 3 case study to just highlight some examples that we have. So the case study 1 is corresponding to the previously called under constraint variables. So here, to be more specific, is like there's an under constraint opcode cases inside our zkEVM circuit. So to give some background context about this bug, is that the EVM circuit is a state machine. So as I mentioned, like each step will correspond to a step you executed in the execution trace that emitted by the EVM. And so that means like every step will have an execution state. So the execution state is almost a one-to-one mapping to the EVM opcodes. But because we want to do some optimization to combine multiple EVM opcodes to a single execution state, so that you can have a single gadget to constrain this category of the opcodes. So to give an example here, so this push is an execution state, but it can correspond to push 0, push 1, and then up to like push 32 from the EVM opcodes. And similarly for the dupe, like the duplicate, like they can be duplicate 1, 2, like a 16, etc. And there's also the call op, like that is basically calling another contract that you can have like different type of calls inside the EVM. It can be like a call or direct call. It can be call code, dedicated call, or static call. You can think like an execution state could be like a cluster of the opcodes in the EVM that are doing the very similar functions, but they have slightly configuration differences, so that you can combine them and then in order to reduce the number of constraints you have in the circuit. And so like there'll be a special register inside this EVM circuit, because in the EVM circuit you can have something like this small state machines, but you have like a few special registers that are tracking, for example, the stack pointers, the size, the memory size, the program counter, etc. And there's like a special register called the execution state. And then that's going to be doing some lookups to match, okay, this execution state is matched to the opcodes. By looking at this fixed lookup tables, basically constrain like the basically like the put like those fixed mapping from the execution state to the opcodes that is like the inside the EVM circuit, inside the Ethereum virtual machines, so the different opcodes. So that would be a lookup here, trying to see, okay, if I can find this pair of lookups inside this responsible opcodes lookup tables. So giving like the current execution state at the current step, and then the opcode. That this opcode is basically read using the program counter from the smart contract you're executing. So you can read this opcode into a variable or a cell inside the Halo 2. Then you do this lookup into this fixed table to see if you can find the matching so that you're in the correct executing state. You don't like constrain like your executing state arbitrarily. And then the error cases actually happens, the bug happens that in some executing state, it can be mapping to multiple opcodes. And especially there's some error cases. For example, this error case state is called error out of gas for SLOAD or SSTOR. So here, like what we constrain is that so the opcode can be only SSTOR, SLOAD, and then you can do the lookup to see, okay, I'm in the correct execution state here. But what we didn't forget to constrain inside this gadget previously, although like this bug is fixed. So we didn't constrain that the opcode is actually correctly reading from the smart contract. So we only constrained the opcode is one of the SSTOR or SLOAD, but we didn't constrain the exact like whether it should be SSTOR or SLOAD given the program counter. So this is something like forgot to constrain. So you can think like, okay, this opcode is already constrained like it's one of these, like it's a pair select gadget. That means like the opcode should be either SSTOR or SLOAD in these error cases. But we failed to constrain this opcode should be like exactly one of them, like exactly one of them, like by reading from the bytecode circuit or lookup tables. So this is something like a fail. So then the attacker basically can fail. It's like it can constrain, like change this opcode to SSTOR or SLOAD, or like changing to one of them. It can all pass all of the circuit constraints. Okay, any questions to the example?
Could you explain the gadget? What is it? And
so this gadget basically is saying like the opcode should be either SSTOR or SLOAD. So it's saying like that. So it should be like, I think the opcode minus like the I forgot like let me think like what is the exact constraint is written in the press, like I mean, like naively you can do like 2 is 0 things, like you can do like compare opcode minus SSTOR value and then opcode minus SLOAD, then one of them is 0, and that's correct. So it can be the pair select.
I was actually asking to see like what does gadget mean here? Like, you have one execution gadget, you have other gadget. Is it like a module or something like that, or like what is the relation of a gadget to a circuit?
Yeah, so the gadget here you can think it's a set of constraints you can apply. So you can think like that. So the gadget taking a bunch of expressions here, and then it will add a few constraints related to these expressions. So these like that will be constant passing to this pair select gadget, and the opcode is one of the expressions for the variables inside the bigger gadget. Then the pair select gadget basically add one or like more constraints around given the input expressions here. Okay, so yeah, so here like I should be like adding additional a few lines to do a lookup to see like look up the opcode and then to matching into the bytecode lookup tables, not matching to the exact opcode that is written inside the smart contract. Inside the smart contract you're executing. Okay, the second case study is the missing ring check. So this is a very typical bugs we will see like usually. So here is a chip which we call the less than chip. Now basically it compare the LHS and RHS and see if the LHS is smaller than RHS, then the LT, there's like a flag output, it should be 1, otherwise it should be 0. So the way like you usually write this gadget is that you will compute the diff of LHS and RHS and then store inside like a few cells here, like the diff here, and then you compare to certain range. It says like the range should be no more than certain bytes. So it can be at most this bytes. Then that means like if you can, for example, you use RHS minus LHS and store into the diff. Then if the diff is within a certain range, then that means like LHS is actually less than RHS. So that is similar. Otherwise, if LHS is bigger than RHS, then the RHS minus LHS basically will wrap around and become a very big number, right? So it will be outside of like the range you have for the number of bytes you can have. So also like usually what we do is like LHS and RHS also have a certain range within the n bytes, so that the diff, if LHS is actually smaller than RHS, then the diff of the LHS and RHS will be within this n bytes range here. So, but the things like the gadget already like did all the things like tracking correctly. But one thing like I forget to do is do a ring check for all of the cells allocated for the diff. So the diff is not like a single value; it's represented in the byte format. So it breaks down into byte limits. So and then you can see like in a constraint like the diff is actually the value equals to the RHS minus LHS. But something like is missing here is kind of typical, is that we forgot to check all of the cells we use to represent this diff value is within a U8 range, within the byte range. So there's something like we missed to do that. But actually, like if you're missing like all of the ring check for the diff cells, you have to represent this byte representation. Then the diff can be arbitrary values. You can think. Okay, so this is kind of like a simple example. Like any questions about this arrow example?
So quick question. I think it's kind of like common for both bugs that you just presented. So it seems like here you have like cases where you don't want the verifier to act, like, you essentially have like, negative test cases for the verifier. So my question is like, do you have like such test cases in your in the code base, or you just kind of like happen to found those like while you're reviewing the code?
Yeah, I think this is like we didn't have the negative test cases, so that it didn't find this. Like it was this bug is found by an auditor there, like when reading the code and find, okay, so they're missing a byte range check. Although I think like sometimes it should be obvious like to add this range check, but like during the development like of complicated circuits, you sometimes just forgot some of the details. But yes, to give you an answer, like I think we didn't have this negative examples for this, like the diff representations, so that like it wasn't found in the first place. Okay, I'll move to like the third one. So this is more like a semantics misalignment with the EVM. So this is one example, is that inside the EVM, when you're doing a static call, you cannot modify any state of the state tree because it's static. So that means like there's a few opcodes. So during the static call, you're calling basically another contract, but this contract cannot do anything like to modify the state. And what if like this contract doing the create, trying to create a create two? So these two like basically trying to deploy a new contract, which shouldn't be allowed, and doing any log, which also modify the state, and then doing a store or call, other things like with argument different than 0. So there's a bunch of the opcodes when doing the static call context. There should be forbidden to modify any state. So according to the EVM specifications, but like so when we write the constraint for the create and create2 opcode gadget, so we didn't check this flag is if that calling context is a static call or not. So the fix basically is to add like these 2 lines is that we need to get a call context to check whether I'm in the static call or not. If it's a static call, like we need to say like it cannot be a static call when you're executing the create or create2. So it should be like a forbidden inside the circuit. So, and then in the actual execution logic, when you do like in the static call, and then you encounter the create or create2 opcode, you should be reverting this transaction because you encounter some errors. So in the circuit, you should forbidden like that this situation should be never happen that you are correctly executing. So this gadget will be only corresponding to the correct executing of the create and create2 opcode. It's not like you shouldn't run into any error cases. Then that means you cannot be inside a static call context. So the fix is quite straightforward. It's basically you will need to add just 2 lines of code. You need to get the call context to see if it's a static call, and then you need to require that constraint that the is static is 0.
Oh.
Okay. Okay. So then, like the last part is like trying to summarize some of the lessons we learned through the whole experience, like a journey for securing zkEVM circuit. And the first thing like I want to say is like we should write down the circuit spec before the implementation. It's always like a good practice. For example, you need to write down how you design your tables, like what are the format, what are the state transitions, and also write down all different logics. So like to see like in certain cases if TXID is 0, like the not 0, like not equal, then what are the constraints you have? So those are the kind of things like, so it will be always easier to find some soundness bugs and some like logic errors in the spec doc other than in the code, because especially in the Halo 2 code, it will become quite complicated to look through the logic. So it's a good practice to write down the spec doc, like the circuit spec, all of constraints you have, and then you verify the logic here first. So it can help you to earlier find any soundness bugs, any logic errors there. And also it will be very useful to review the code, because you can always compare your code to the spec you have and see if there's any missing constraints. And because we did see like an example that so the engineer write down the spec correctly, but during the implementation it missed 1 or 2 like the constraints from the spec. So during the implementation it's like easy to forget. So it's always good practice like to write down the circuit spec first. And then the second thing is like do extensive testing. So and then the things like you should have is like a reference implementation that you can always like generate a bunch of different cases and to verify to get a correct witnesses that you can have, and then you can put that into the testing cases to test if the all of the circuits written correctly. And then also as like in the last question mentioned that it's very valuable to have negative test cases. Although sometimes it's very hard to find all the different negative cases, but it should be like it's very helpful, like valuable to have negative test cases and expect that the circuit will fail to prove. So if it passed like those tests, then that means like there's some soundness bug you didn't check. But how to get like a good coverage of negative cases of different corner cases, because there's so many possibilities. You can change any values like by 1. So it's very easy to construct a negative test cases, but it's hard to do is like to find a good set of negative cases to hit most of points there. Because like when you write a very complicated circuit, so you get most things right, but just missing 1 or 2 constraints. So it's pretty hard to find a negative cases to hit that point, because it's so easy to captured by other constraints you have inside the circuit. So this is a challenge job, but it's still like good practice to write down the negative cases and try to think hard what are the things that you should consider in the negative cases. And then it's always good, like valuable to have more pairs of eyes look at the code. That could be like the open source, like by the code review by the open source community, or finding external auditors to look at your code to read your code, and security expert like using bug bounties or those friends. Like it's always good like practice to have more eyes of the code. More pairs of eyes to look at the code. And also another thing like sometimes like will be missing is like to understand if the proof system is sound. And also if any optimization tricks that you have applied is sound. So it could be like something like you're usually missing. For us, like I think the Halo 2, they did also some internal, they already gone through all of the reviews. So the proof systems like they should be also better tested by different projects. It's good like that, but you still like need to be careful. And also sometimes you're using the libraries, like if for any library, there could be like bugs inside that. So it should be like always good like to be cautious about anything like you're using, like you build on top of them. And also like something like I think future should be like helpful is like more automated toolings, especially for the circuit. So I think like there's a lot of automated toolings for smart contracts, for other like the software like Go or like a Rust program. Like they also have automated tooling to help you find some common bugs. I think we are still lacking more automated toolings for the ZK circuit, especially. And for example, there's some ideas like you can fairly easy like to have a tool to read through the circuit to see is there any variables you didn't constrain at all, like there's something like easy to find. And also sometimes like we have like is that if you find the one type of bugs, and if like your circuit has like the similar part, you can do like some semantics graphs, so to find the similar patterns you have like inside other circuit, you can just go through that. If like matching those patterns, because you hit like one place, it's likely like there's some other things like that have the similar errors there. So if there's certain like things like it can help you to define some patterns and then just search through the code base to see if there's other places hit the similar patterns, the bug you find. So that'd be also helpful. So there's some like ideas like I have like this brainstorming, and and the last part would be like just formal verifications. So it's very tricky like to formal verify a circuit, but I think like if you have the formal verification of the circuit, then it will give you a strong guarantee, so that you can do some like model checking on the circuit and see like if you hit all of constraints, all of the possibilities can be constrained like in the circuit. Sorry, does someone have some question or comment?
No, I don't think so.
No.
Yeah.
Okay, cool. Yeah, actually, like that's like almost like what I have for this presentations. I'm open to any questions you have.
Hi, Haichen. I have a question. I'm Shankara. So it seems like there's a lot, like you had to write 90,000 lines of code to build this EVM, or to build this ZK VM specifically for EVM. But like presumably if you want to later target some blockchain that's not EVM compatible, you might have to do all this work again. So like can you maybe talk about like any effort going on in the community for something like, let's say you had like an LLVM for blockchain VMs, and then you can do all this for just one architecture, and then let's say compile the proofs and thing to like these other VMs. Is there any kind of agenda project going on that would make it easy to sort of like build these roll-ups for multiple architectures, multiple VMs sort of simultaneously?
Yeah, so I think there's a few efforts there. Is that I know, for example, the Neo Foundation, they're building the zkEVM, so that essentially you can, using the LLVM compiler to compile, then you can generate a ZK circuit automatically for you. I'm not sure like how good like it could be. Like it could be initially like not very well optimized. Like you can generate like a not so efficient program by using the zkEVM. The circuit might be like not very well, not very efficient. Then you can like have some like hits, but maybe like through over the optimization over iterated like over the time, it may be like very easy to do that. And another thing is like the, for example, there's people like building for the zkEVM for example, the risk zero, they're building the zk, like the risk VM, so that if you can compile your program like into the risk instruction set, then you can basically execute on the risk VM. Then that execution trace will be constrained by the risk by the zk risk circuit inside that. So you don't need to even write a circuit for that program. You just need to compile into the the risk 5 instruction set. Did I answer your questions? Okay.
Yeah, I think so.
Okay. 5 years. Do you see multiple zkEVM that makes performance trade-off? Parallelized efficient prover comma. Do you see more layer to convert to a single zkEVM project? I think like still there'll be multiple zkEVM project, and that also like not only for the I think like the people were trying to keep optimizing their zkEVM circuit, and the performance wise will be similar. I would say like over the next 5 years, and then probably like keep iterating and optimizing. So it'll be like bring down the cost and then the time to do the proof generation for the zkEVM. But I would say like it still won't be like a single zkEVM project. Especially like I think it will be powerful to have multiple zkEVM implementations, so that in the future you can have multi-prover, so you have different zkEVM implementation to verify that. It will give a stronger security guarantee.
I have a question about like the automated tooling that you mentioned at the end. I thought it was also like a good closing because like our participants have already played with some of our automated tooling, over Secureum. So I think like, one of the challenges we kind of like face when we try to generalize like our solutions to like, arbitrary frameworks like, Hello 2, Plonky, and so on and so forth, is that when you have like a circuit like written in this kind of like general purpose like languages, you just get like a set of constraints at the end of the day, right? And then you kind of like lose the modular structure of like, the code that generated like, these circuits. So do you believe that like, if you had like a different format that was like maintaining like this structure, so first of all, would it be helpful even for like, debugging these circuits? And second of all, do you believe that like, a project like zkEVM would kind of like, be willing to kind of port to this kind of like, more complicated format?
Yeah, I think that would be valuable to have some of the intermediate representation of this of your constraint systems, so that different system can all like exploit into this intermediate representation of different constraints. Then you can apply standard like things that can generally apply to different front end, and also it also helps you to connect to different backends. So if you can all like the compile down into some representation of the polynomial identities, then you can also then more easily to connect to different backends. So I think that's something like it's very interesting like to pursue in the future. Although I think like there's some project I remember like they're mentioning like the interested from Halo 2 community, they are interested in building this, separating the front end and the back end. So the front end is basically the circuit arithmetizations, and then you can output into some intermediate representations, and then you can then connect to different backends. And then this intermediate representation then can be applicable to different automated checking toolings, so that I can check like apply to all of different front end circuit.
Okay, yeah, I mean that's definitely interesting to us as well. Because like, I mean, we have like, we have the techniques. It's kind of like the issue we have is kind of like the loss of precision when you just like, get like a table at the end of the day.
Yep, makes sense. Yeah.
All right. Any other questions? All right. So let's thank Haichen for the great talk again. It was like really nice to have you.
Yeah. Thank you for your attention. And very nice to give this sharing in this workshop. All right.
Thank you so much. Okay. Have a good day. Bye.